And thank you for organizing this wonderful workshop. It's really a pleasure to be here. You're going to hear a lot of the same themes that we heard from the earlier speakers come up in this context. So it's really wonderful to get a chance to draw us all together, since I think there's a lot of commonalities, especially in what I'm going to talk about next. So while the previous two speakers apologized for very abstract, overarching talks, I'm going to apologize for the opposite extreme, which is too much nitty-gritty detail in scientific practice. I'll try to go through that relatively quickly, but since some of this might not be familiar, I think it's important to keep it grounded in some practice to build up some of the cases I want to talk about. So I'm going to begin by sort of revisiting some work on data models and talk about what I think are some of the strengths and weaknesses of the previous approaches. And then I'm going to dive into the scientific case study. Being a practice-oriented philosopher of science, I want to keep what I say grounded in practice. So I'm going to look at how paleontologists are trying to construct curves or draw conclusions about paleodiversity from the fossil record. And so I'm also somebody who's trained in the history of science, so I'll be doing a little bit of history in this part of the talk as well. And then I'll take us up to the present with the corrected approach to reading the fossil record, which I'll talk about in detail. So then I'll look at contemporary practice and three approaches for how paleontologists are using models to correct the data. And then I'll try to draw some general philosophical lessons for that, including relating it to some things that were said earlier today by other speakers. And I'll conclude, if I have time, by highlighting what I think are some parallels between data in paleontology and data in climate science. Data in climate science has gotten a lot of attention recently, and I think it's important to sort of show that we find similar practices in other areas of science as well that aren't, that are less controversial. So we'll do that if we have time. So as you know, we must begin with our discussion of data models with Patrick Suppes, his classic paper 1962. I think he's right to challenge the simplistic view that there's just data and theory which are directly compared, and that rather than raw data, scientists are primarily interested in model of the data. And he introduces this important notion of a hierarchy of models. And so I think those were all important steps forward in our thinking about data. One limitation, however, is that Suppes' account is built on this Tarskian notion of a model as a set theoretic structure, what's been called the instantial view of models. And so he says, I claim that the concept of model in the sense of Tarski can be used without distortion as the fundamental concept in all disciplines, the same in the empirical sciences. And then he goes on, and I think this is something that's not, while this is well known, I think this is not always recognized, that he also thinks that models of the data should also be understood in this instantial Tarskian sense. Models of the data are then defined in terms of possible realizations of the data, as should be apparent from a logical standpoint. They're defined in just the same way as possible realizations of the theory. And so it's this view that I think that we should move away from or reconsider. Okay, now many people have challenged or criticized Suppes' notion, the instantial conceptions. Ron Geary, for example, in discussing his theoretical notion of a model, says, I want to call my understanding of models representational because it takes model not primarily as a means for providing, interpreting formal systems, but as tools for representing the world. But what's interesting is in this same paper, when he gets to the section on data models, so he discusses data models also, that whole criticism just sort of disappears. He doesn't quite realize that, or it's not evident that he embraces his notion, Suppes' notion of data models without really mentioning the instantial versus representational debate, nor its implications for our understanding of data. So I think that's sort of been overlooked. This happens also in Sabina Lianelli's excellent book, so Data-Centric Biology, a wonderful book, again, really advancing our understanding of data. But she sort of cites Suppes without sort of thinking about what the implications of adopting this instantial view of data models might lead us to. Okay, so despite many citations, I think this notion of data model is still under-theorized. And I think there's more work that needs to be done in the philosophy of science examining this. Okay, so moving on to Lianelli's work. she has 3 key characteristics that she identifies for data, and I agree with most of what she says, and I think we can see it in the case of paleontology that I'll be talking about today. So her first point is that data are material artifacts, that the materiality matters. So their concrete characteristics, the format medium, are relevant to our understanding their epistemic role. So we certainly see this in the case of the fossil record. So throughout history, we've sort of seen the notion, the materiality of the fossil record changes. So initially, it means literally the rock fossils that were collected in various museum drawers and cabinets around the world. Later, this became abstracted and put into volume collections that are descriptions of the fossils in various ways. So these large compilations of volumes with, again, a different material vehicle for representing the fossil record. And most recently, we have things like the paleobiology database, which is a computer representation of the fossil record. And so, and again, we want to be thinking about the materiality when we're evaluating these different components. Second, she notes that data are not given but constructed. And again, I think this is a crucial insight, that data are the result of a complex process of interaction between researchers in the world. And down in the bottom right, we have a picture of a fossil preparation lab. So even the very fossils themselves are constructed. Fossils have to be prepared in various ways, the matrix removed. I'll come back to talk about that in a little more detail later on. So even at the very basic level, the data of the fossil record is constructed through our interactions. And data are defined by their evidential role ascribed to them in a particular context. OK. Now, where I want to part company with Leonelli's view is that she rejects data models as representations. I want to argue that data models, like theoretical models more generally, should be understood as representations. So now I think that the idea that we should think of them as representations has been rejected for the wrong reasons. So when I say that data are representations, I don't mean that they are perfectly accurate depictions. So I want to draw a distinction between a depiction, which is supposed to be sort of this perfectly accurate, versus a representation, which certainly can involve all sorts of idealizations, distortions, and so forth, even fictions. So it doesn't mean that they're perfectly accurate depictions. It doesn't mean that they're mind independent when I say that they're representations of the world, nor does it mean that they're fixed in their evidential value. So I think those are sort of her motivations for rejecting this view, but I think we can accept that data models should be thought of as representations without falling prey to those concerns. Second, she says, I want to argue that data are representations that are constructed through complex interactions of the world. And the idea is the hope that they carry some information about the world, right? That's why we collect data. We want there to be some correlation with the world that we are trying to measure. And the idea is that the hope we can extract some of that information about the system of interest in a way that can be distinguished from various artifacts or noise. I think that third here, the hierarchy of data models, it should be understood as a branching hierarchy of representations. So there are different ways that these data models can be abstracted and idealized and processed and repackaged in various ways. So it's not just a linear hierarchy, as Supa has talked about, but even just at the level of data models, we can see that there are different ways we can process this data. And finally, whether the data are an adequate representation is not something that's fixed, but rather depends on the particular context and use to which the data are being put. So to tie in with some Wendy's earlier talk today. OK, so now why is it that I want to move away from the instantial conception? As you mentioned earlier, it's a very broad conception. Almost anything can fit into it. Why would anyone want to reject it? Well, I think there's some good philosophical reasons to do so, namely in that it creates a problem, I think, at least the way that it's been articulated by people like Supes and von Frazen, that we run into this problem that, and here I'll quote Frigg and Nguyen, who says that Supes was the first to suggest that data models are the target of scientific models. Models don't represent, here he's talking about theoretical models, don't represent parts of the world, they represent data structures. Thus, on this view, models don't represent planets, atoms, or populations, they represent data that are gathered when performing measurements on planets, atoms, or populations. So we'll see that this gets developed with von Frausen and what's called the loss of reality objection. The concern is that if we just have this instantial conception where we have the set theoretic structures that are related, where the notion of representation is one of an isomorphism, we can run into this problem where we can only represent these different levels, these different models via isomorphism, but they don't quite reach the ground of the world. And I think that's a problem. And the representational view is a way to make that ladder reach all the way finally to the ground, because our representations are about the world and are allowing us to draw conclusions about the world, and that we miss that on this instantial view. Okay. So I think that's a philosophical motivation for moving on. And we see this same concern arise in the context of von Frausen when he discusses the loss of reality objection. So he gives this example of a deer population graph. And he says, well, suppose that a scientist presents a graph of the deer population growth and points out that some theory T provides models that fit well with the structure displayed on the graph. And he says, imagine that there's somebody in the audience who raises their hand and says, but wait a minute, we're not interested in whether the theory fits your graph. We're interested in whether the theory fits the actual deer population in the world. And in response to this scenario, von Frausen responds, he says, there is no leeway for me in this context, short of withdrawing my graph altogether. Since this is my representation of the deer population growth, there is for me no difference between the question of whether T fits the graph and the question of whether T fits the deer population growth. Okay? So now I pick this because I think it relates very closely. The sort of deer population growth curve, I don't know why my laser pointer's not really working here, but that we see over here on the right is very similar to the sort of paleodiversity curves that the paleontologists are trying to construct. And I think this is quite wrong about scientific practice, this idea. And again, I think it comes from this sort of instantial conception and this failure to sort of reach the world that is important, and that the representational view can help us do better. So representation for him is just isomorphism. So it's not the sense I'm talking about. So what are the problems here? So when a scientist presents a graph of a deer population, what she is asserting is that it is a representation of the deer population. A representation which she is very aware could be idealized, incomplete, or even in some respects a distorted representation of the actual deer population. So if confronted with this interlocutor in von Frausen's example, it would likely go into great details about the ways in which it's accurate or inaccurate, the parts of the graph she has more confidence or less confidence, the potential confounders that may have not been adequately controlled for, and so on. And I think that this is important for understanding scientific practice, is that we think of these graphs as representations of the world. They're not supposed to be perfectly accurate depictions. They're supposed to be representations that are going to be limited and inaccurate in certain ways. Okay, and that scientists can often tell us quite a bit about the ways that they think their graphs are inadequate. So von Frausen asserts, what I cannot do, here's the quotation, I cannot do is both present the graph as representing something and say that perhaps it doesn't represent that at all. And I want to say that that's a false dichotomy. It's not the case that we either have a representation, here a representation is being thought of as a perfectly accurate depiction, or we don't. It's in respects and degrees, and that's important. Okay. So, in some cases, scientists may only have sort of a hunch about what those respects and degrees are. They may not be able to tell us all the ways in which it deviates, but they'll be able to, in many cases, tell us that there's a confidence in certain respects. Okay, so again, representation doesn't mean perfectly accurate depiction. So let's look at the scientific case now, and I'll begin with a little bit of the history. So I'm going to argue for looking at the case of paleontology and the history of biodiversity or paleodiversity over time. And these views about how paleodiversity has waxed and waned over time, from things like the Cambrian explosion when diversity was high to mass extinctions when diversity is low, scientists are interested in constructing these graphs mapping those variations in paleodiversity over time. Now, where these graphs come from is the fossil record, right? So you look at how many fossils you have in certain time periods, organize it into the various taxa, and then you sort of do these counts, and that produces what's called sort of the raw taxa diversity estimate. It's not actually raw. I'll talk about that later, but it's often referred to in that way. Now, what's interesting is that the fossil record is something that scientists from the very beginning have understood is incomplete, it has inaccuracies, it's biased in all sorts of ways. So, for example, we have Charles Lyell in the Principles of Geology saying, quote, "We are bound to remember whenever we infer the poverty of the flora or fauna of any given period of the past from the small number of fossils occurring in the ancient rocks, that it has been evidently no part of the plan of nature to hand down to us a complete or systematic record of the former history of the animate world. Such failure may have arisen not because the population of land or sea was scanty at that era, but because in general the preservation of any relics of the animals or plants of former times is the exception rather than the general rule." Okay? So here we have a very sort of frank statement that we have to be careful in trying to read paleodiversity off of the fossil record, because from the very beginning it was understood that that record is biased in various ways, and incomplete in various ways. So we also see this in Darwin. So Darwin, of course, was in a situation where he wanted, on the one hand, to be able to use the fossil record as support for his theory of evolution by natural selection, but at the same time, he was very worried about the incompleteness of the fossil record, in that people could use it to say, we don't find this continuous gradation of forms, therefore your theory is wrong. So he was really sort of struggling with how to deal with the data of the fossil record in his account. And he, in The Origin of Species, he devotes an entire chapter, chapter 9, on the imperfection of the geological record to try to sort of make excuses of how we need to be careful in trying to read paleodiversity or read evolutionary hypotheses off of the data of the fossil record. And it's a theme that reappears in several other chapters as well. So this is a very lengthy and dense sentence. Actually, there's 2 sentences here. But you can see that he's really, I'm not going to go through all of it, but what's interesting is sort of this period of time, people who are interested in trying to read biodiversity from the fossil record really had this sort of pessimistic attitude about how much we could glean from it, right? And how it could be used to support more general theoretical hypotheses about evolution and so forth. So Darwin goes through great pains to try to articulate the various sources of bias in the fossil record. And what's interesting, he does a very good job, actually, of it. So he says the fossil record is extremely imperfect. Only a small portion of the globe has been geologically explored with care. So we see that this is kind of an anthropocentric bias, right? So most of our fossil record comes from Europe and North America, whether other parts of the globe are very, very poorly explored. So he says only certain classes of organic beings are preserved in the fossil state. So obviously, soft body organisms, soft body parts don't get preserved as well, and so forth, depending on their ecosystem that can affect it. The number of specimens and of species is nothing compared in our museums, is nothing compared. The deposits have to be thick to resist future degradation. Enormous intervals of time have passed, so these things could be eroded away again if they manage to get brought to the surface. They can be destroyed. The sediment in which fossil rocks forms is not continuously deposited. Only certain environments, so swampy environments, tend to be well preserved with sediment, but other sorts of environments are not. And the duration of formation might be short. So it goes through this very long list of all these biasing factors. And so he says the geological record, extremely imperfect, will explain why we do not find interminable varieties connecting together all extinct and existing forms of life by the finest gradual steps. Okay, so with both Lyell and Darwin, we have sort of this pessimistic view that we wanted to be able to try to, the fossil record is a unique and tremendously important source of data about the history of past life, but at the same time, it's just riddled with all sorts of biases. It's incomplete in all sorts of ways. The great caution has to be taken in trying to draw any broader, to use this as evidence for any hypotheses. Okay. So the list of things that Darwin talked about is not unlike what we would find in a standard textbook about paleobiology today. So today, these are often called, these biasing factors are called filters. So if you think we have this sort of biological signal of paleodiversity, And then we have various biasing factors that filter that signal and distort that signal in various ways, or delete portions of that signal in various ways. So there's anatomic filters, biological filters, ecological, sedimentary preservation, metamorphic, so forth. There's all these different things that come into effect. Okay. Now, so there's a wonderful book by the historian David SubKoski, his book Reading the Fossil Record, where he talks about these different stages of how scientists approach the fossil record. And he talks about the notion of a paleobiology revolution that was very much tied to the introduction of computer simulations into paleontology and the creation of these large-scale databases as playing an important role. So he tells the story is going back to a small group of paleontologists, Stephen Jay Gould, David Raub, Thomas Schopp, in the early 1970s. They were gathered together for a conference on modeling at the Marine Biological Lab in Woods Hole, Massachusetts. And the idea was then to see what could be done about this problematic fossil record in terms of being able to sort of bring paleobiology that was merely descriptive before into a more quantitative science. So one of the outcomes of this meeting was sort of a renewed optimism about the fossil record. So SubKoski talks about this as an idealized reading. I don't think that's quite right. I'm sorry, as a literal reading of the fossil record. I prefer sort of optimistic reading, because I don't think they were saying we should actually read it literally. But one of the papers that came out of this meeting in the early, I think it was 1971, was the famous paper by Niles Eldredge and Stephen Gould, their punctuated equilibrium. And here they tried to say, look, they talk about it as this sort of self-imposed inferiority among, compared to the other sciences of paleontology. And they want to say, no, many breaks in the fossil record are real. It's not just sort of an artifact of its incomplete nature, but we should actually read this a little more literally. We should then say that we should resist this gut reaction to view almost any anomaly as an artifact imposed by an imperfect fossil record, and they suspect the record is better than tradition dictates. And so then they use these breaks to argue for the punctuated equilibrium view. And this optimism, this is David SubKoski's father, Jack SubKoski, who was a paleontologist involved in these, so he's a little family history here in his book. And SubKoski was a graduate student at Harvard working with Gould. And in 1973, Gould sets him the task of going to the library and going through all the journals and books that he can find and see how many orders within classes, families within orders, and I'm sorry, that was genre, I got autocorrected, within families over the last 600 million you could find. So trying to get a massive database of the fossil record by going through all the different sources, trying to standardize it, trying to delete duplications, trying to get some tally. And he describes this as, there's a paper he calls 10 years in the library. I mean, talk about a cruel dissertation director setting a graduate student with this kind of a project. It's a miracle he ever got his PhD. Anyhow, so he came up with this very well-known figure, the SubKoski curve, describing how paleodiversity changed over time. And again, it's sort of this optimistic movement or wave within the history of paleontology. This curve was important. So he was able to discover 3 distinct fauna, the Cambrian, Paleozoic, and modern, that dominated the fossil record. The big 5 mass extinctions started to become clear. So there was certain things for which even this incomplete, impartial, and distorted fossil record was adequate for learning about the history of paleodiversity. Now, what's interesting is that we also see, with the rise of these computer simulations and the introduction of these models, the Marine Biological Lab model, the code was actually written by SubKoski when he was a grad student, even though he wasn't listed as an author of the MBL papers. They wanted to sort of run these highly idealized stochastic equilibrium models that were detached from all historical detail, that were sort of devoid of substantial biological assumptions. And the idea was to treat taxa as particles and they would generate an initial lineage, which was then randomly subjected to either persistence, extinction, or branching in a sort of Monte Carlo simulation. And then it was depicted graphically as a phylogenetic tree. And these simulation models, and so when Gould talks about replaying the tape of life, it's this computer simulation model that he has in mind. And what their strategy was is they noticed they could produce these phylogenetic, representations, trees that looked very much like the real ones. And so they were sort of, this is curious. Here we have, something that's very idealized, and yet it can provide at least a visual representation that's strikingly similar to the real thing. So Thomas Schopp sort of initiated another strand of approach to reading the fossil record, which is this idealized approach. And the idea was, well, maybe we can learn some things if there were these laws. So he wanted to sort of think of it as this sort of a particle paleontology, that we could have these sort of gas law, this very, very physics sort of picture of the history, and we don't need to worry about all the messiness of the biological details. And so the idea was that these simulations could then be a replacement for the messy detail of the fossil record, and what sort of conclusions could we draw about the laws governing these patterns there. So that particular approach was not very long-lived, and the MBL simulation model sort of outlasted that particular interpretation, and instead it became used as what I'm going to call a subtraction model. So the idea is to sort of say what part of the pattern can be explained from these simple hypotheses, and then what is the residual that can't be explained, and that we need to have more substantial biological hypotheses. And this notion of a subtraction model is going to come back again as being important. So so we had the pessimist phase, then we had the optimist phase, that we can just read things off. And then we had, let's just give up completely and go the idealized route. The final one is what I'm going to call the corrected approach to reading the fossil record. And here's sort of a balance between the optimism and the pessimism. And it still makes use of the computer simulations of the idealized approach. And it was championed primarily by David Raup, pictured here. And the idea is that, here is a picture of the actual, the idea is to use the simulation model to construct a hypothesized biodiversity curve. So this is, let's say this is the initial actual curve, but it's hypothetical. And then to think about putting into the simulation model various biases and looking at what curves result. And so these are the curves that are resulted after the various biases that Darwin listed, the various filters get imposed on that initial data. We see that the curve gets shifted in various ways. So in this paper, he was primarily trying to argue that, that this increase that was observed in marine diversity was an artifact. But what was more interesting, I think, for our purposes, is the way that he was sort of approaching using these simulation models as a way to think about the effects of the biases on the actual biological signal that the scientists were interested in. So now he does there's kind of this problem that we can get what looks like our observed biodiversity using the simulation model to argue there was really a different paleodiversity initially. Okay, so he says, undoubtedly there are other plausible models as well, depending on the weight given to each of the biases. So he sets paleontology on the following task. He says, future research should therefore be concentrated on a quantitative assessment of the biases so that a corrected diversity pattern can be calculated from the fossil data. Okay? So he says what paleontologists should really be trying to do is to try to get a quantitative understanding of what effect these biases have on the paleodiversity curve. And if we can do that, then we can figure out how to undo their effects. We can correct the fossil record data. He thought that computer simulation models would be a good way to do this. Okay, so traditionally taxonomic diversity was just raw counts of taxa, as we saw before. There's all sorts of problems with just doing sort of the raw counting in each of these bins, time bins, and sometimes it depends. There's large sample sizes, so what are called Lagerstätten are well-preserved sites. So the Burgess Shale is an example. periods where we have these sort of Lagerstätten sites, there's lots of diversity because it's very well preserved. And then there's some time periods in which there aren't these sort of well-preserved sites that we know about yet, at least. And so we have these different sample sizes across different geological time periods, and so they can't be directly compared to assess diversity over time. So what's interesting is that Raup then suggests a second method for correcting. So the first method was the introduction of these computer simulation models. A second method that he introduced was known as rarefaction or subsampling. And that's something that has been developed to a high degree of sophistication in contemporary paleontology today. So this is now taking us up to the present. So we see that this corrected approach is the one that's dominant in paleontology today. It's one that uses computer models and simulations to correct the data in various ways. And what we see is that there's several different methods for correcting the fossil data, and that they all use models in some way or other. And I'll try to lay that out now here. So the first correction method is known as subsampling or rarefaction. So the idea is to try to correct for biases that arise from difference in sample size. So that was the second one that Raup had identified. In the classical approach, it was assumed that a fair sample was one that was uniform. All the samples had the same number of individuals. But more recently, John Alroy, paleontologist, argued that when diversity is high, when diversity richness is low and a species is very common, you don't need to sample much to find out what there is. But when diversity is high and a given species is more rare, you need to sample harder to get an accurate picture. So this idea of imposing this uniform size would actually produce a distortion in the correction. So he argued that, that a different method should be used. I won't go into great detail. It's a horrible name. Shareholder quorum subsampling, or what ecologists hate that term, and they tend to use coverage-based rarefaction method. It actually goes back to some early work of Turing and Good at Bletchley Park, developing some models for when you don't know a lot about the underlying population, being able to draw some inferences. So they use that mathematical work to develop a subsampling method in paleontology here. Okay, so we have different approaches now to trying to correct the fossil record. These different approaches have different theoretical arguments for and against them. But in addition to sort of these theoretical questions, we can also try to test them with computer simulations. So as Raup initially suggested, we can think about taking a simulation model, introducing a hypothetical paleodiversity, right? Say we know what the original paleodiversity is by hypothesis, right? Then we use these two different subsampling or rarefaction methods to delete various portions of the fossil record and see if these subsampling methods are able to recover the correct initial curve. So, and they then were able to show the various scenarios under which these correction methods, which correction method worked better, under what conditions did it work, under what conditions did it fail, and so forth. And obviously there are problems for subsampling. There's simply some taxa are unknown. It assumes random sampling, which doesn't hold in real data. And sometimes the taxa data is just too sparse to impose subsampling. So there's limitations to this method. So that was one approach to correcting the fossil data. A second one is known as the residuals approach. And so the residual approach, what it tries to do is, remember we talked about the different filters? The idea is to try to construct a model to represent the effect of a particular filter. So at the bottom, at the yellow here, we have the biological signals that we're interested in order to test our theoretical hypotheses, the data that we want to be able to use for various purposes. And the problem is that that biological signal got filtered. The blue box here is the geological filter. And then there's also the sampling filter, which has to do with the paleontological effort in their collecting, right? Maybe paleontologists are more interested in charismatic species of fossils than other sorts of fossils, so they collect more of those anthropogenic biases as well. Okay, so the idea then that Smith and McGowan proposed is to do a data correction method, and you construct a model in which you say, okay, what if let's say the rock record, the rock outcrop area, and that actually is including, so it's our measurement of the rock outcrop area, so it's also sort of reflecting our knowledge and the biases that come from our investigation. What if we take that to be a perfect predictor of the sample diversity? And then once we can get a model of that, we can use that in the subtraction way to delete that portion of the signal from the paleodiversity signal that we have. So we have our raw taxic diversity estimate that we do. We know that this curve that we get from the fossil data is biased in various sorts of ways. We know one of major source of bias is the rock record, right? So let's model the rock record. Let's say the rock record, see if we can model that and say if that were a perfect predictor, what would the signal look like? We then subtract that, and the hope is that the biological signal will be left behind. Does everyone? Feel free to stop me if anything's unclear. OK, so the intuition is that this residual, so that's why it's called the residual approach, is the part of the paleodiversity signal that's unexplained by the rock outcrop area, and hence by sort of a Mills method of residues is attributed to the genuine biological signal. OK, so again, we're looking at how models are being used to correct the data in various ways. So there's a whole family of residual model approaches. There's a question of what should be the sampling proxy that's used to represent the geological filter. So there's different ways that that can be made. There's also different ways to construct the residual modeling. So Graham Lloyd said that we shouldn't assume a linear relationship between the observed diversity and sampling proxy data. Instead, he suggests nonlinear models and then use the Kake information criterion to choose among those. So we have different competing approaches to correcting these things. There's also a problem that was pointed out in the literature that we have to be careful in that the rock record, variations in the amount of sedimentary rock deposited, right, which is the geological signal we're subtracting from the biological record, could have a common cause, right, in terms of climate change. And so we have to be careful in that we might be subtracting actually some of the biological signal by pulling out the geological signal in this way. So sea level changes affect both diversity and the amount of sedimentary rock. And so in this common cause hypothesis, we have to be careful that we might be pulling out too much from our diversity curves. OK. But what I want to point out again is that these questions are not intractable, right? So we have ways that we can try to determine, distinguish between the common cause hypothesis, what direction the influence might go. And when we have these multiple, we have the Lloyd method and the Smith and McGowan method of using the residual approaches with different proxies, we can test these things using simulation models. So Neil Brockerhurst in 2015 looked at 8 different methods for carrying out the residual diversity estimate, and he said one clear result is a rejection of the Lloyd method. So the Lloyd that used the nonlinear and the Kake ended up performing worse in recovering the hypothesized initial biodiversity signal, paleodiversity signal, no matter what sampling proxy was used, and the Smith and McGowan method did better. So scientists are figuring out how to sort of get a handle on which of these correction methods is actually doing a better job of recovering the initial signal. OK, so here's a picture of the simulation model approach. You have localities containing a taxon from the bin, localities not. You delete the taphonomic filter, remove some of these. So some places where we had, these were all filled in here, and we've deleted some of these here. And then there's a second filter that's related to sampling. We're deleting some of the entire boxes, and so forth. So this is running a simulation model that performs this. Again, you start with a paleodiversity that you know initially. You impose these filters, these biases, and then see how well the correction methods recover the initial. OK, so now what he concludes from these studies is about the different sampling proxies. He says that using more restricted sampling proxies produces, he says, a worse representation of the history than the raw data. So so using a more restricted sampling proxy produces a residual diversity estimate further from the true diversity than an uncorrected diversity curve. OK, so that makes it worse. But it produces highly dispersed results, which are a worse representation of the history than the raw data. OK, so he says, I think this is important to sort of note that he's talking about this notion of representation, a representation of the history of biodiversity, and questions about which of these data, the corrected or uncorrected, is a better or worse representation. So there's no belief here that we can have a perfect depiction of paleodiversity. There's no attempt to the one true paleodiversity curve. That's not in the offing for these paleontologists. But there's idea of having better and worse representations of the history of paleodiversity in various ways. And he identifies the optimal among the different methods. So he says optimum implementation of the residual model approach to correcting consistently outperforms the raw taxic diversity estimate. So he says, yes, the residual corrected data is better than just the raw counting. It provides a better representation of the true history of the clade than the raw data. Okay, so a third approach, which again uses models to correct the data. So we've seen subsampling, we've seen the residual approach, which tries to model the filters. The third class of correction techniques for the data are known as phylogenetic approaches. And here the idea is to use cladistic analysis and phylogenetic tree models to correct the gaps in the fossil record. So cladistics is a method for inferring ancestral relationships using characters. And on the basis of the similarities and differences, you construct a cladogram in which it's assumed that a group of organisms is related by descent from a common ancestor. And when a lineage splits, it divides exactly into two sister taxa, which appear at the same time. Now, this last assumption is important for the phylogenetic correction method in that it licenses an inference that any taxon is as old as its sister in this branching. So what we often find in the fossil record, I'll come over here. So here's the actual relationships, let's say, for the branching of the various clades. So time comes along, and this is what the paleontologist actually can observe. We have this taxon here, this one here, this one here. And what they do then is they say, OK, we can infer that there had to be some branching in the past. And what they do is they call this a ghost lineage. And that they'll infer that this is if it's the sister taxa, if C is the sister taxa of B, then we can extend, even though this is where the fossil record goes back to here, C's fossil record doesn't go back as far as in time, that you infer that it must have gone back to the point at which they branched off. Okay, so you can fill in what's called the ghost lineage, and here's another ghost lineage here. Now, so again, here we have at time T2, this is where taxon A appears in the fossil record, B goes back to T0, and we can infer the ghost lineage of A must go back as far as B if it's a sister taxon there. And so it's the idea of using these phylogenetic models to correct the data. And we know that if that's correct, then we have that we should infer that even though there's no fossil representations back at this point in time, that it must have been there. And this leads to very different diversity curves. So if we just take where we actually have fossils present at certain time bins, we'll construct a diversity curve that says up until time T2, we had a lower diversity, and then the diversity increased at T2 when A appeared. So that's the raw taxic diversity estimate. Whereas the phylogenetically corrected paleodiversity curve will say, no, we've actually had diversity remaining constant throughout this time interval. OK, good. So now there's the phylogenetic approaches. There's different ways of doing this. Another a way that it can go forward, those we're looking at ways to correct it backward in time. Going forward, there's what's called a Lazarus taxon. So the famous example of a Lazarus taxon is one that disappears from the fossil record for a long time, suggesting that it's gone extinct. But then a representative appears again millions of years later, or even as a living specimen. So the coelacanth is a famous example where it's in the fossil record from the Devonian until the Cretaceous, and there's no representatives in the fossil record of the coelacanth after the Cretaceous. They just don't appear. And then some fishermen caught a specimen off the coast of South Africa, and so what they realize is that, sort of back from the dead, the Lazarus idea, there must have been a ghost lineage that we can infer. So given our understanding of evolution, and that there has to be this continuous lineage going all the way back in time. So that's a way that we can correct the fossil data also there. OK, now obviously the phylogenetic correction methods are only as good as our cladistic models, as our phylogenetic trees. These, of course, can be revised in light of new data. So it's not like this is an infallible method. So we need to take that into consideration with these correction methods, but we can have more or less evidence, like we do in any other part of science, for these corrections. Also, it's the case that ghost lineages can be extended forward or backward in time, as we saw with the two cases. But in most cases, it's extended backward in time. And so there's an asymmetry in the phylogenetic correction method in that most often you're increasing diversity one direction, but not the other. So extinction times are less likely to be extended forward. So the point here is to realize that when we're thinking about these data correction methods, we also have to try to investigate what are the biases that the correction method themselves can introduce into the data and try to get a quantitative handle on that as well. Okay. So he says, well, rather than thinking of the phylogenetic method as an alternative to, let's say, the subsampling or the residual method, we should instead adopt a pluralist approach where multiple methods are used in concert to correct paleodiversity. And then also, he says, secondly, we should use, again, computer simulations to test. So he says, we show here that this is a study by Lane et al. This included SubKoski that I mentioned before. It was published posthumously. He says, we show here in the majority of diversification scenarios, similar to the phylogenetic method, the PDE, the phylogenetic correction method, is superior to the taxic, the TDE, which is the raw. However, the expected backward skew in diversity that we talked about, the correction method tends to skew backwards, is apparent in many circumstances, and this includes time intervals leading up to an event horizon such as mass extinction. So the simulation models talked about which correction methods are better, right? It talked also about what sort of biases, the bias that we expected this correction method, the PDE method, to introduce was revealed in the computer simulation, that indeed it does have that bias. And they were able to sort of locate where that bias typically appears, namely in leading up to a mass extinction. So where is it that we should trust the phylogenetic correction method? Where is it that we should have a little more skepticism or caution in interpreting it? Now, this idea of the PD, leading to look like a gradual decline prior to a mass extinction event, the phylogenetic correction method exacerbates that problem. And this, of course, is a well-known issue in the case of the extinction of the non-avian dinosaurs with the Chicxulub asteroid impact that led to their extinction. The people were arguing, was it the asteroid that did it, or were the dinosaurs in long-term decline prior to the asteroid? And so the asteroid was just sort of the icing on the cake, the final thing, tipping point, straw that broke the camel's back. And so you can see that these kind of considerations about how to interpret the data and see where these biases are sort of very important for understanding these sort of cases. Okay. In these simulation studies, he draws a number. This is going back to the Brocklehurst. He says, first, the phylogenetic diversity estimate shows a better correlation than either residual or the raw taxic diversity estimate. So that was one of the best performing correction methods. Second, although the correlation of the phylogenetic diversity with the true data decreases with worse sampling, the rate of decrease is less than with taxic or residual. So as the sampling gets worse, how much does it start to deviate? We can measure that for these different approaches. And he notes that the phylogenetic diversity estimate appears remarkably resistant to errors in phylogeny. So remember we said that that correction method is only as good as the phylogenetic tree that you're using, right? If it's not an accurate phylogenetic tree, correcting to that tree is not really going to help you. And so what they did again with the simulation models is to see, okay, let's assume that we get the tree wrong in various ways and look at how that affects the data. And they were able to show that the method is resistant up to those errors. Okay, good. So we're done with all the science now. I apologize for all that detail, but I wanted to sort of get a sense of the practices and what's going on and how models are being used at every turn in the looking and constructing these data models. Okay. So what are some of the general philosophical lessons that we should draw from some of this work? Well, I think, first of all, we need to just reject offhand two unhelpful views, right? If we're interested in trying to develop a philosophy of data that's answerable to scientific practice, there's two views about data that we should reject. One is that data are just an unmediated window onto the world whose epistemic reliability is given. You had this as the naive view that you dismissed off the hand, which is correct, good. This view fails to distinguish data from the world, suggesting that data just are reality, right? And that's obviously a mistake. There's a wonderful quote from the theoretical biologist Robert Rosen here. He says, any measurement, however comprehensive, is an act of abstraction, of replacing the thing measured, the natural system n. Why did he use n? That's always a number. But anyways, that's nature, by a limited set of numbers. Indeed, there can be no greater abstraction than the collapsing of a phenomenon in nature down to a single number, the result of a measurement. From this standpoint, it's ironic indeed that a mere observer regards oneself as being in direct contact with reality, and it's theoretical science that alone deals with abstraction. So again, as a sort of early insight to this idea that measurement involves an abstraction, we need to be aware of that. So we can reject that first view. A second view that, again, is unhelpful for understanding scientific practice is that data are merely abstract set theoretic structures that can only be related via isomorphisms to other abstract set theoretic structures. This view also fails to adequately distinguish data in the world, but this time it's the world that's lost. And we saw this with Van Fraasen's lost reality objection. And the problem with Suppé's semantic view that we never get that ladder to reach all the way to the ground. OK. So I want to argue that the notion of data model, if it's going to be helpful for understanding cases like the paleontological case, it needs to be disentangled from the semantic view. The representational view that, for example, Wendy's defended, Mark, you talked about it this morning with your talk, emphasizing the representational role, is something that we should extend to data models as well. Data models are representations that are constructed through complex interactions, and their value precisely as they purport to tell us something about the world, right? They carry some of that signal. The fidelity of the data model is not something to be assumed, but assessed, and this project of assessing, correcting, improving the representational adequacy of the data model is at the heart of scientific practice. And you talked about this in the iterative process, and we see that very much in the paleontological case. So we're continually trying to improve that diversity, that SubKoski curve that we saw with these methods. And Suppé was right to say there's a whole hierarchy of data models, but these should be understood as a hierarchy of representations, on my view. And he was, of course, interested in how data relate to theory, and I'm focusing more on the hierarchy of data models just within the data section of that hierarchy. OK. So, and again, this data model hierarchy, I think it's important to sort of realize the plurality of ways that the data can be corrected, that we have this branching. It's not a simple linear hierarchy, it's a branching hierarchy. And we see that in this constructed nature, even at the bottom level of the data model hierarchy, in the paleontology case, the fossil rocks themselves. So this is a picture. Here's that fossil at the end came from this. Right? So they start with this chunk of rock. The matrix is the name for the rock that's not part of the fossil. You can just barely, you can barely tell. It takes a lot of expertise to see that there's something there. And then through this process, though, this is a time series of the different, as they slowly carve away the pieces, you end up with the fossil specimen at the end. So this is a constructed data model. So even the fossil itself is a data model. And there's a lot of theory, right, and expertise that goes into producing the fossil rock specimen itself that's in a form that's useful for scientific theorizing. And I think it's important to see that we can see that even at the level of the physical data. It's not just the given, right, even at that level. So there's Caitlin Wiley has a number of wonderful papers on the importance of fossil preparators. So these are the people who prepare these fossils in the fossil preparation lab are not PhDs in paleontology. These are skilled laborers whose job it is simply to remove the matrix, and they don't have a PhD in paleontology. The paleontologist is not allowed to touch the fossils. There's a definite separation of work here, a division of labor and expertise. They have their own societies, their own methods. It's often described as sort of this tacit knowledge, how to do this. And so forth. So she has a wonderful series of papers on that I recommend. And she's really calling attention to the importance of this and how it's non-trivial to produce a fossil specimen in many cases, as you can see here. And there's a wonderful quotation here. So she recounts, so she sort of was sort of like an anthropologist going to these fossil preparation labs, listening to these, the preparators talk about their work. And there was a joke in one lab about how an accidental slip of the instrument could lead to the discovery of a new species, right? You accidentally nick off one little part, and voila, the paleontologist who gets the fossil, who then starts to theorize it at the end, would say, oh, this is a new species that we didn't realize, this new genre of trilobite. So she notes that there's often difficult decisions that the preparators have to make in distinguishing what's signal and what's noise, right? So how do you know what's matrix to be removed and what's the fossil signal that you want to have preserved? And she has this wonderful observation. She says, scientists recognize the underdetermination of knowledge by data. They know that there's multiple interpretations of data possible, and as a result, interpretations must be defended. But reminding them that the specimens themselves are underdetermined by the raw material, that specimens may take different forms and yield different data depending on how they're processed, is more dangerous because it threatens the natural objects that are the foundation of empirical research. So we have this idea that even in the physical data at the sort of the lowest level here of our fossil record, we have to be aware that there are these questions about how we process this. And she talks about how fossil preparators often are reluctant to prepare a fossil more than is required for the paleontologist theoretical question. So the preparator will say, what information do you want to get out of this? Only prepare the fossils to that amount, because the more they remove, you can't recover it, right? So they only want to remove what's required at any given stage. So there's these kind of questions about how this process takes place that's important. Again, emphasizing the data are not just given, but constructed even at this lower level. Obviously, then we need to categorize it taxonomically. We need to arrange it in chronological order. Lots of theory involved in constructing these. There's substantial biological, evolutionary, anatomical theory and extrapolation from incomplete specimens and information that goes into creating each of these levels. So there can be legitimate scientific disagreements about the right way to sort of climb this data model hierarchy, right, in various ways. And we need to be aware of that. And one thing that Wendy's brought up in previous cases is we often think of, a plurality of data model representations, that's a weakness. We need to find the one correct way to climb the ladder. But there's cases in which this could actually be a strength also, and that we sort of see, all right, there's different ways we can climb, correct the data. Are there certain assumptions that are common across these different ways of preparing the data that are supported regardless of which way we climb the ladder? So good. OK, so looking at drawing some analogies, again, with climate science, I'll come back to this in more detail. But this process of sort of collecting the fossil data together and to try to construct this picture of biodiversity over 600 million years or whatever it is an example of what Paul Edwards in the context of climate modeling calls making data global. So certainly this is something that climate scientists are struggling with. How do you build a complete, coherent, and consistent global data set that could be used for drawing, testing theoretical hypotheses and so forth, from very incomplete, inconsistent, and heterogeneous data sources? And that's the same problem that paleontologists are confronted with as well. So, and one of the points that Edward makes is that there is this model data symbiosis. So at every level in the data model hierarchy, as we saw from the rock specimens themselves all the way up to the paleodiversity curves, is going to, the phylogenetic corrected global data sets involves the use of models at each stage. There is thus this model data symbiosis, whereby models and data are in a mutually dependent but mutually beneficial relationship. So this notion of a model data symbiosis, I think the notion of symbiosis is supposed to be a beneficial relationship, right? We often have this view, don't mess with the data, that if you come in and correct it with models, you're corrupting the data. And here we're seeing a very different picture, right? This idea that models are required for, think of the rock of the trilobite, right? If it's going to be useful for scientific theorizing at all, we have to construct the data model, right? That's how, models are how the data becomes useful for scientific theorizing, that it's not. So Stephen Norton and Frederick Suppe say to be properly interpreted and deployed data, it must be modeled. And they further argue that whether physically or computationally realized, all data collection from instruments involves modeling. Now, there's two ways you can interpret that. I would say I would take a more moderate interpretation, not to say that there's no distinction between data and models, but rather recognize the complicated ways in which data and models depend on each other. OK, so drawing some conclusions now about purity versus fidelity. So traditionally, it's assumed that the purer the data is, the more epistemically reliable it is, the less it's been corrupted with our processing in various ways. But I think in the case of paleodiversity and fossil record, we see just the opposite, right? As the simulation models showed, the residual corrected fossil data did a better job of tracking the true paleodiversity than the raw fossil data did. And the phylogenetically corrected data was even more reliable than both the residual method, corrected method data and the raw data. And so I want to sort of reject this knee-jerk review that the purity of the data is a measure of its epistemic reliability. That's just wrong. I think we see the opposite is the case. So in his discussion of model data symbiosis, Edward notes, instead the question is how well do scientists succeed in controlling for the presence of artifactual elements, both in theory and observation. And this is how the iterative cycle of improving data proceeds. So I want to say it's not the purity that matters of the data, but rather the fidelity. And again, thinking of it in this representational way. OK. Another important distinction that I think is helpful for understanding cases like the paleontological one is this distinction between physical control and vicarious control. So we just saw in the Edwards quotation that he talks about it's controlling for artifactual elements in the data that we care about. Now, Physical control is what we typically do when we set up and design a lab, right, experiment, right? We want to try to shield from various sorts of noise. We want to shield from, let's say, the Earth's magnetic field, air currents, radiation. We want to physically remove some of the biasing factors that could come in through friction or purifying the sample. So physical control, we're all very comfortable with as being allowed, right? We don't want just the raw data. We want data that's collected very carefully in this controlled physical environment and where we've shielded from these things. In many cases, so like in climate case, in the paleontological case, we are not able to do physical experiments, right, in the lab, right? We're dealing with a historical science. We're trying to take data that we can't sort of reproduce in a lab situation. So we can't use physical control. And the idea of vicarious control is the removal of unwanted effects after the experiment is conducted by measuring or estimating their influence and then removing them, we'll say mathematically, during data reduction. And there's been a lot of focus on physical control, but I think this notion of vicarious control is important, right? And that in many cases, even when we talk, and so Norton and Supe give an example of even in some laboratory experiments, it can be so difficult to shield the thing that you want to shield from that they choose not to do it physically. They choose to do it by measuring its effect and then modeling it and taking it out subtraction models. So there's cases in which even when we, in theory could do it physically, the choice is we can do it much better, much more easily vicariously. Okay, so good. So I want to say that, I think there's Wendy, in case you don't know what she looks like. And I think, that we've had this distrust of vicarious control, and I think it's important to realize that whether physical control or vicarious control is reliable has to be assessed, right? We can't just assume that one of these methods is reliable and the other one isn't. It has to be assessed in any given situation. All right. And next, I think that it's important to recognize the fidelity of one's data in representing some facet of the world need not be all of nothing, but is a matter of degree. And we certainly see this in the paleontology case. So the key question is not whether the data model is a perfectly accurate depiction of the world, but whether it's a representation that's adequate for the purposes to which the data model will be put. Okay? So what sort of theoretical claims is this data supposed to be providing evidence for or against? That's the key important question. So Wendy has argued this very cogently in the case of theoretical models. And I want to extend this again to the case of data models. I think we should talk about data models as being adequate for a purpose, and that we should be investigating what are the various purposes for which a given data model is adequate or inadequate in a particular case. So, in the case, connecting this point of adequacy for a purpose back to the paleontological case, even at the level of the fossil specimen, how the rock is prepared will depend on the theoretical uses to which it's put. We saw in section 2 that the raw taxodiversity models were sufficient to provide evidence that the tempo and mode of evolution didn't always proceed by gradualism, but Elridge and Gould punctuated equilibrium. So we saw even the raw data was able to answer some sort of questions. It was adequate for that purpose. However, that raw taxodiversity data models were not adequate for the purpose of resolving whether the non-avian dinosaurs were in a long-term decline prior to the asteroid impact, right? That the data was not adequate for those theoretical questions. And that there was papers arguing that phylogenetically corrected data is what's required in those cases. And so the paleontologist Benton et al. And colleagues argue or write, quote, the fossil record, error-ridden and incomplete as it is, which is a theme we've seen from the very beginning, is adequate for many purposes, although none of these provides evidence that the error in the fossil record is negligible. And so again, this dichotomy that we saw with von Frausen, either it's a representation or it's not. I have to withdraw it. It's a false dichotomy. We say it's a representation that's adequate for some purposes, but not other purposes. And we need to say, even if it's error-ridden and incomplete, there may be questions that we can answer. And there's techniques we can use to correct that data to make it more adequate for answering other sorts of theoretical questions. Okay. So you might think that, well, look, we can't travel back in time and learn what the true paleodiversity is. This seems to be that we're always going to be in this epistemic situation of not being able to know whether we're getting closer or farther away, so there's sort of this skeptical challenge. Now, I think what we see in the case study is the ingenuity with which the paleontologists have made these seemingly intractable questions tractable. right? So they've, first of all, come to understand in growing detail, from Lyell forward to contemporary paleontology, the contours of our ignorance about biodiversity, the ways in which it deviates. Second, they've developed a suite of methods for correcting the fossil data. So we've seen 3 different methods illustrated here today. And third, they found ways to test the reliability and robustness of these methods under our ignorance, right? So using the simulation models to say, how well do these correction methods work? Now, again, you could say, well, testing it in a simulation model is not a perfect indicator of how the correction method is going to work in the real world. But you could say that it's a minimum constraint, right? If this correction method can't perform well in a simulation context, starting with the hypothesize, is not likely to work well in our case. So it at least, I think, starts to get us closer at any rate. OK. So to summarize, data models should be disentangled from the instantial view. We should think of them as representations. Representation does not mean perfectly accurate depiction. Rather, what's important is its adequacy for particular purposes. Third, the naive intuition that using models to correct data would somehow be a corruption of the data is based on the false assumption that the purer the data is, the more epistemically reliable. As we saw, however, it's the fidelity, not purity of the data that matters. The fidelity of the data is improved by learning to identify, then control, shield, or compensate for the various sources of distortion or noise. This can happen either physically in the context of our laboratory experiment or vicariously in the process of data reduction. And the reliability of both physical and vicarious controls is something that needs to be scientifically investigated and assessed in any given situation. So we can't just say one is always more epistemically reliable than the other. We need to look at how well they're performing in each of these cases. So then just looking ahead to some parallels to conclude. Climate science and paleontology, both fields are trying to construct global data sets from incomplete, inconsistent, heterogeneous data sources. Both sciences are interested in a highly constructed variable, right? So the temperature of the Earth or global paleodiversity. Here's the number that represents the paleodiversity at this time period. That's a highly constructed variable. The sort of data that these sciences require cannot come from controlled experiment in a laboratory setting where physical controls are added. They must instead use vicarious controls. And finally, in order to become scientifically useful, the data must undergo substantial filtering, interpolation, and correction in an iterative cycle of data model improvement. And so models and computers simulations not only make this possible, but also give us a window into knowing when and where these corrected data models are adequate representations for our purposes. And I'll stop there.